Kostryukov from Voronezh State University, Voronezh, Russia. The invariance and mechanism of the many-particle multistep nuclear reactions and fission.
Dear colleagues, I report today the lecture about T-invariance and mechanism of many-particle, multistep, reaction, and fission. The main aim of my work is to use the T-invariance condition for many-particle multistep nuclear reaction, whereas A to B, whereas A have A sub n particles and the Bm particles in the final channel. To distinguish possible mechanism of this reaction, to throw violated mechanism of T-invariance and to only analyze these systems. Firstly, we consider the T-invariance condition for quantum mechanical system, the unified. To this, we used we write Schrödinger equation 1, and this equation have two solutions. First solution is psi which is one function, original function, and the time reverse solution psi sub z. The psi sub z have explained by equation 2, whereas tau is an operator of time reversion. He represented by operator k of complex configuration and the unitary operator which is satisfactory for condition the next condition 4. Now we gain only Schrödinger equation, stationarily Schrödinger equation, and represent the matrix element of arbitrary operator by 6. As we see in formula 6, we have the transition from time reversed matrix element and the operator of matrix element have been expressed by formula 7, whereas we have two options, two projection, only doing operation 7 by 7. In this case, the set of operators, for example, operators of coordinates, moment, orbital moment, and spins has been expressed by formula 8. In this case, we expressed the function psi as form to pretend which expressed by formula 10. as we see, we have minus p and minus of projection of spin, because we need of this, because the operator of time reverse operator added to the function this way. Now consider the amplitude of investigated reaction. This amplitude can be written by formula LR. As we see, we have initial non-perturbated function of initial channel and the final wave function of final channel B. This representation has by form has by T matrix form, whereas T is a operator, reaction operator, and can be read by formula Pavel. As we see, we have in this formula two interaction potentials, which can be added to the function, and they transition below to matrix elements. After that, when we used all previous formulas, we can form to the T invariance condition for amplitudes. Sorry, just forgot. I forgotten about introducing amplitude for inverse reaction. Inverse reaction, we able to find some conditions which allows to pretend some features. The form is analogously by form origin initial reaction, but we have transition the wave function of f sub a to f sub b. As we see, the operator T tilde have another form, either the operator T of original reaction. Just see that the interaction potentials of initial and final channel can be transverse, reverse. After that, after introducing, we can write T invariance condition for matrix elements of initial, original, and time reverse reaction. This form can be written by formula 16, where psi sub a and psi sub b can be replaced by the time reverse reaction of these states. If we have some conditions to the energies EA and AB, we have rewrite the operator reaction operator in unified form. It's as you see, we have only dependent from full Hamilton of system and full energy E, which we have in equation for stationary state of Schrödinger equation, stationary Schrödinger equation phi. In this case, we have some interesting feature that the form of reaction operator is equal, and hence we have simple view to the simple view of T invariance condition for amplitudes. As you can see it in equation of 20. You see that we only replace the final and initial channels and inverse the impulse momenta and projection of the spins of channels. Plus we product multiplying to the phase. Now let's consider the cross-section of differential cross-section of this reaction. This cross-section can be can be expressed by formula 21. As we see, we have the spin density matrix of initial channel of reaction AB and amplitudes of this reaction, unified amplitudes. If we have if we have reverse reaction, the amplitudes, the operator of amplitudes can be equal. The operator of reaction, can be equal, and the states of reaction, of course, are different. Then, if we have, if we taking into account the definition of reverse reaction or conjugate reaction, which means that the matrix, density matrix have equals to the density matrix equal density matrix of initial channel A in reaction AB is equal to density matrix of the final channel of time reverse reaction. It's very important because we must go to begin if we time reverse in the time reverse operation. The cross section of this reaction can be expressed by can be related the equation 22. As you see, the cross section proportional to the cross section of time reverse reaction. It's now we considered the asymmetries of in reaction, because in experiment in the experimental works views the asymmetries which confined by formula 23. For the original or initial reaction, this coefficient dBA can be written as this form with signs plus or minus corresponds to orientation of certain vector arbitrary vector parameters which we study. And now we, because of formula 21, we can see that the function of the asymmetry dBA can be represented as function which depend from spin and momenta of final and initial channels of reaction. Because other spins goes down. Its function represent this scalar or pseudo-scalar function can be represented like this in common case, and only after the using T invariance condition for the differential cross sections 22, we can see that the reactions asymmetry coefficients dBA and asymmetry coefficients for original and time reverse reaction functions. These functions can be unified form because we transit from initial. We have one set of interactions, and we goes by the time reverse, and we have another. We have unified set of the potentials. If we have, if this condition are verified, that we can reproduce these coefficients by the same form. And T invariance condition for these asymmetries can be rated by equation 24. Now we derive in experiment derives asymmetries by T even or T odd. What is it? When we have T even asymmetries, we have we replace to the initial states time reversed states and time reversed function. As we see, if this asymmetry coefficients doesn't change to the sign, it's T even. Else T odd. Now have this determination we can use to the T invariance condition, and we see that the T even or T odd when the T even we only transverse the states A, B, and we don't change the sign of this symmetry, of this coefficient asymmetry. Else we have minus of this asymmetry coefficient dBA. Now some interesting. Now we can get these results, and just see these asymmetries in fission, binary and ternary fission. For example, these asymmetries can be there have in differential cross section of binary and ternary fission can be next asymmetries. P and PLF, SN PLF, and others. These coefficients, as I say, it's a scalar function, name about scalar function. Use the T-invariance condition for this asymmetries. What we see? We have by the condition we must transverse final and initial states and inverse the values change to sign. As we see, if this after this, if we have sign plus, we have T-invariant asymmetry. All these asymmetries is T-invariant, but one of these not invariant, because they have odd minor, because of her T even T odd. What we can do is this: if this asymmetry T non-invariant, there is there to be zero, but this asymmetry was found, and they are not equal to zero. And what we can do is very simple. If we consider the if we have representation of ternary fission, because this is symmetry of ternary fission, non-arranged target nuclei by polarized neutron. If we we have a representation of two-step reaction. The first step of reaction is departure of capture of neutron by target nuclei, and the second step is departure of all three particle, third particle and two fission fragments. But as we see, if we have this representation, this asymmetry is equal to zero. But if we have another representation, if we present the ternary fission as a third step process, we have another answer. We have T-invariant asymmetry. Why? Because in vector product we replace impulse of third particle and light fission, because third particle departure early either either the compound nuclei decay. And we have T-invariant asymmetry. Everything all right. Now, we have after that we have an instrument of the we have an instrument to bring some mechanism and distinguish some mechanism and we have some mechanism cannot be adhere one, and the next I soon done. If we consider another correlations in the asymmetry, we have interesting thing that the sum of these asymmetries can be T non-invariant. As you see, if we have reactions, fission, ternary or binary fission, polarized, oriented charged nuclei and polarized neutrons, we have these asymmetries, and if you to do after that actions for the which requires the invariance condition, we have seen the one few of that have minus, and it's very interesting. Because if this asymmetries we can found, we found the violation of T invariance in strong forces. Thanks for attention. If you somebody understand what I say, I answer your question.
Thank you. Any questions?
Any question?
So what's your conclusion? Is there violation of T symmetry?
Maybe, because we don't know equal to zero this, for example, this or not, because it's theoretical. It's very complicated experiment to do this. Research the return the fission of polarized.
I understood you that you said at some moment that some asymmetry coefficient is definitely non-zero.
Yeah, of course.
This is not yet enough to conclude that the T symmetry is broken.
No.
Not yet.
No. These coefficients compound to the cross-section of all reaction, and they cannot be zero. But some asymmetries must be to zero, or else it's T invariance violation.
Okay, is this within the experimental possibilities of the time of our time? What is the estimate upper bound on this coefficient? You say that according to modern experiment, we may say that this is less than something.
Yeah, you just say what I must say. If we found this correlation, we have estimate the T invariance violation. I answer of your question.
No. According to the existing experiment, you may or may not state that according to the present data, this coefficient is less than something, than some value, which depends on the experimental accuracy.
I don't ask this question. I ask another way. This not experiments of this correlation haven't been.
There was no...
No, because it's very complicated, because it's polarized, investigate polarized neutron, oriented charge nucleus, and
Okay, so you propose this experiment as a criteria
yes,
of T invariance.
for example, because this T even and P even, nothing to terms which can be higher estimate. Ну, короче говоря, там будет самый точный. Он будет иметь, как раз вот та штука, которая измерится, этой корреляции, она будет давать как раз ту самую погрешность на нарушение этой invariance.
It's clear. Then,
you mentioned in the last slide that are some polarized neutrons. How can get away such neutrons polarized?
By a magnetic field.
But neutrons are neutrons.
They have spins. Spins. They.
This must say that is oriented but not polarized. No?
It's maybe a definition, but yeah, it's strongly oriented. If that have say.
But I believe that at the very, very small scale also neutrons might be polarized.
Cold. If the temperature below to zero, it can be. The experiment P parity, for example.
Yes. In my yesterday exposure, I mentioned that possibility of have polarized neutrons. Thank you.
And,
let's think. Okay.
Oh, sorry.
Let's
No
send
question?
to the other questions. Let's thank to the
Thank you
speaker
for attention. Thank you for question.
and pass to the following presentation.